Good day, everybody. Today we're going to look at finding the center of mass of a hanging chain. So Galileo hypothesized that the shape of a hanging chain would be a parabola. It's actually not quite a parabola. It's close, but we'll see there's a curve which does better than the parabola in that it'll have a lower center of mass. So I'm going to focus on finding the center of mass of a curve, and to do that we need to find the average y value of the curve with respect to its arc length. And we can think of that as a line integral problem. So we want to, if you want the average y value, integrate y ds divided by 1 ds, which will just be the length, of course. So if you have the parameterization, this will be our formula for the average y. So let's look at the parabola, and we'll compare it first to kind of the straight line, two straight lines, sort of an absolute value shape. So the first thing I'll do is I'll find the length of the parabola curve. You know, we want all the curves to have the same length for fairness. So if you picture y equals x squared, from x going from -1 to 1, y prime's 2x, and then the arc length is the square root of 1 plus y prime squared, so it'll be 1 plus 2x quantity squared. So there's the arc length. We can actually get it exactly if we prefer. Root 5 plus 1/2 log of root 5 plus 2 is one way to put it. So there's the arc length right here. Half the arc length, I call it L2, but it's really L over 2, is this value. And then b is the square root of half that arc length minus 1. So what that is doing, let me look at our absolute value graph. So obviously in blue is the parabola, y equals x squared. There's the origin right here. And then in red is the absolute value. It'll have the same length. So that's why I wanted half of the arc length. That's sort of this value here, and it's kind of the hypotenuse where one side has length 1, right? If we go from -1 to 0, that has length 1, and then this height I called b. So b squared plus 1 squared is L squared, and so that's how I solve for b. It's the square root of that hypotenuse squared minus 1. So this vertical amount is b. 1.09 almost. And so you can see I have the equation then, b times absolute value of x minus b plus 1 gives me that absolute value. It'll have the same length. And now let's find its center of mass. So to do that, I integrate the function times the square root of 1 plus y prime squared. Well, the slope is b over 1, negative as from here and positive here, but either way b squared will be the slope squared, y prime squared. So y prime squared is just b squared. It's not differentiable at 0, but that's okay. We can still do the integral. And so the center of mass is going to be at 0.4552 almost, which for a straight line, the average y value would just be the middle y value. So I can verify it by, I know this whole vertical length is b, so b over 2 is half the length, and if I subtract that from 1, that'll be the middle value. So 1 minus b over 2 is the same value. A little bit of rounding error, but. Or if I do 1 minus b puts me to where this y value is, right? 1 minus b. And then if I add b over 2 to that, that's what this is. So 1 minus b is the bottom, add b over 2, that's this value too. Right? So we know for straight lines the average y value will just be the middle y value. Right, so there was the integral, and then after I divided by the length, I got that y value. Well, for the parabola, if I do the integral times this ds, then I get this value, and then if I divide by the length, I get 0.41. So it's got a lower center of mass. In fact, here's the difference. It's about 0.045 lower. If I plot the two center of masses, well, it's hard to tell the difference there, but I'll plot with the curve. So the center of mass of the absolute value curve is there in red, has this height. I made it extra long, but it'd be above 0. And the center of mass of the parabola is there in blue. So if you have a hanging chain, you pull it straight down, you're actually going to increase its average y value. You can see obviously the bottom y value goes lower, but all these y's are above those y's. So it pays to go down fast a little bit, but if you go down fast a little bit, you're not going to go down as far. So there's some balancing there. The parabola is almost has the minimum center of mass, but by a little bit less. Let's see what we can do. We can do the hyperbolic cosine. So here is going to be the hyperbolic cosine function that'll go through the points negative 1, 1, positive 1, 1, just like the parabola, and will have the same length as the parabola. So the hyperbolic cosine curve is in red, so it actually doesn't go down as far, but it goes down faster, but not too fast. So I mean, there's a balance there, and that hyperbolic cosine wins. Right, so here we're looking at the graph. Let's get these numbers now. So to get those numbers, I'll go back up. I'll just hit me start here. There's the length that I want. That's the length of the parabola curve. And this will be the length of the hyperbolic sine, of the hyperbolic cosine curve in terms of a value A, which is this value right here. So I'm kind of free to choose that, and changing that will change the length. So I solve for A so that the length was exactly what I needed. So there it is. This will be the arc length. All right, so this is the arc length of the function I'm going to have. It matches the arc length of the parabola, which I repeat down here. And if we want it exactly, there's the exact value. I can raise or lower the hyperbolic cosine, and I needed to raise it so that the endpoints were at 1 and were at 1 when x was negative 1 and positive 1. I need the y value to be 1. So that's what this b value does that I solve for. And just to check, if I do f of 1, yeah, it's 1. Checked it. So the red curve has the same length as the blue curve. They match at the endpoints. And now for the center of mass, you integrate the function times the ds, which will just be this. The center of mass for the parabola, the function times its ds will be this. So there's the two y values for the center of mass, and the one for the parabola is a little higher, 0.40, I mean almost 9, but this is almost 0.41. In fact, well, so if I subtract the two, this is how much higher the parabola is than the hyperbolic cosine, so it's actually not too much. And if I plot them, well, here, if you zoom in, it looks far, but if I look at the curve, unlike with the absolute value, now they're one on top of the other. But the red is a little lower than the blue. If you zoom in enough, you would see that. So that's the average y value. This gives us center of mass. The endpoints don't have to be the same height. It'll be a hyperbolic cosine no matter what, if you look at a hanging chain. Here's a video of some hanging chains that match the hyperbolic cosine curve. Not the most interesting thing, but see, so they don't have to be the same height. It'll be a hyperbolic cosine, and you can always match. In fact, I mean, I made the curves first, and then no matter how I put the chain, as long as I can always make it so that it'll work out. It just shows they're not glued or anything. All right, so hyperbolic cosine. That's the favorite. Is it glued? No, of course not. It's just hanging freely, matching perfectly. So that's what I see when you drive behind a truck or whatever. You see hanging chains, you should think, yep, there's another hyperbolic cosine. Just to compare, we just did the average y value with respect to arc length s. But we can do it with respect to x, but that won't give the center of mass. And just to see how things look different, I will look at what happens. And now we had this factor for ds that we need, because most curves you can't get an arc length parameterization too easily. Technically one always exists, but you can't really find it analytically. But if you could find the arc length parameterization analytically, you could actually just do this integral if you had y in terms of the arc length. But again, that's not too easy to do. There's a couple curves you can do that to. Coincidentally, one of them is the hyperbolic cosine. Another one's a circle. So just pictorially, I have both here. This is first the average with respect to x. And the average y value is going to be pi over 4. Maybe I'll come back to this integral in a bit, and we'll take a look at the picture. So discretely, what the picture looks like is I take, say, 20 points equally spaced. So this is the unit, top half of the unit circle. And if I take 20 points equally spaced and average them, they're going to be close to what I'm calling the average with respect to x. And the more points you take, the closer it's going to get to pi over 4. That's what I'm saying is the average with respect to x. Like, I'll double the number of points here. So if, this is the number in the first quadrant, so there'll be 20 in the first quadrant, but 40 total. So if I take 40 points equally spaced, average them. Well, let's see. So here is if I average the 20 y values, I get 0.788, which is very close to pi over 4. In fact, it's 0.002 away. Or if I do 40 points, which is n equals 20, but this is in each quadrant, so there's actually 40 points. Then I'm getting closer. Here it is at 1,000. All right, so it's getting closer. The more points you have, the closer you're going to get to pi over 4. The graph's not very good if you do 1,000 points equally spaced. Let me take it back to 10, just to compare with respect to arc length. Okay, so that's 20 points equally spaced along the x-axis. Find the y's, average them. It's not too far from pi over 4, and then the more points there are, the closer you are to pi over 4. Now, with respect to arc length, what that would look like, well, so here's the integral first, which we can picture a certain way. like this if we want, but I won't focus too much on picturing it like this. Basically, here's the curve, and then there's the y value as a height. Maybe I'll come back to that, but here's actually the way I want to think of it. So if I put 20 points equally spaced along the curve, that looks like this. Now, what it's going to converge to is the integral ds. And that's going to be 2 over pi. And that's a smaller value, 0.64, as opposed to 0.78. So you get a different average. All right, so there's the 20 points. If I, well, so here's how close it is to 2 over pi, but it's already really close, actually at 20. It's amazing how close it is. But at 500, it'll get even closer. So you're converging to 2 over pi. If we look at the graph, this has both. So the asterisk or stars is if you're equally spaced along the curve. The circles were equally spaced along the x-axis. So you can see you have kind of more points lower if you go equally spaced along the curve. Whereas if you go equally spaced along the x-axis, you shoot higher, faster. And then up here, there's kind of more points, more circles, I mean, with respect to the x-axis than there are stars. So it's a different average, right? So just think of if you're a person and you walk this hill, if you took your average every few steps, you would find your average height with respect to arc length. But someone else, if they did it with respect to your east-west position or something, they might do it with respect to x. And you get 2 different values that way. Similarly with the hyperbolic cosine curve, just kind of look quickly here what the plot looks like. You'll maybe trust these averages. So the arc length, I'm just going to do the right half of the hyperbolic cosine curve. Points equally spaced along the x-axis look like that. Okay, so you can see they look farther apart as it gets steeper. And what it's converging to sinh of 2 over 2. It's already really close, just with 10 points. And here it is with 1,000 points. It's really close. You know, go to, I don't like the scientific notation. Let's go to 500 points. There it is. So you're converging to 1/2 of sinh of 2. If you take points equally spaced along the curve, you converge to this value, which I put right here. We won't go through the math of that, but that's what we're going to converge to. It's a higher value, if I remember right. And here's its plot. So these points are equally spaced along the curve. Still 10 equally spaced along the curve. And so we're already pretty close to that value. If I put them together, well, there's more values. Don't worry about that. If I put them together, you can see the, with respect to x, had more lower points, I guess. Is that right? Yeah. And with respect to s, had more higher points in this case. And, well, you might say, yeah, that's true with 10 points, but, you know, what if there's, you know, 1 billion? They're going to be so on top of each other, but the average, it's almost like a density then at that point, right? Like how many points you have along a certain range. So it doesn't matter how many, well, the more points, the closer you're going to get to that integral average. And those integral averages were different values. 2.1 and 1.8. So those matter. Again, here it is with 10. I can maybe make it 20. So there's 20 points. If I do it over here, 20 points. So there are 20 points equally spaced along the curve instead of along the x-axis. So we're close to the claimed average, around it's around 2.15. Plot the 20 points of each together. I get more circles lower, and then it stretches out, whereas with the asterisk, it's kind of evenly spread. And no matter how many points you have, the average is going to be different. Just 2.16-ish for along the curve, 1.81 along the x. A quick look at the math if we want to realize that we can do an arc length parameterization. First I did it for the hyperbolic cosine, our last curve. And you can do it either way. You can think of it as y as a function of x, or you can think of it as a parametric curve with x equal t, y equal cos t. I mean, they're identical work here. So y equals f of x is just a special case of a parametric curve. And then the arc length formula for y equals f of x looks like that. Or for a parametric curve, it looks like this. But of course, if you have x equal t, you'll get a 1 here. And so you get the same thing. It's kind of redundant to do both, but I did it anyway. And then if I find the arc length in terms of the upper limit b, I've gone s units if x is b. Or solving for x in terms of how far I've gone, it'll be like that. And then if you want to find the y value, it's hyperbolic cosine of x, but there's this identity. So if I replace cosh with the square root of 1 plus sinh squared, then the sinh of x is now just s. So that's how you parameterize it right here. Note with that parameterization, dx ds, dy ds will have magnitude 1. Right? If I take the square root of dx ds squared plus dy ds squared, it's the square root of 1. So it means you're moving at unit speed. So you have to know how to differentiate that. Actually have that work, but won't worry about it. If we want to see it here, if I look at my window, I'll go negative 2.2 to 2.2, and there's the hyperbolic cosine I can trace. Go to 0, and x is t, so they're always going to match. And I can go to 2.2. That's how far I graphed. If I look at the other curve, this is the same curve, but now it's the arc length parameterization. And I'll keep the window the same, negative 2.2 to 2.2. And it's the same curve, although it doesn't show as much. If I trace, let's go to 0. So that's my starting point. So an arc length parameterization is unique up to your starting point and direction. And now as I move, the t value, I can't use s, so the t value is how far I've moved. And then where I am is the x and y below. So I've moved, let's go to 1 unit. So after I've moved 1 unit, that's the x and y. And if I go to 2.2, that's how far I've moved along the curve, the hyperbolic cosine curve. Again, we can do it for the circle. There's a generic circle. Find the arc length parameterization. You know, most curves, you won't get it analytically. I won't run through the math here if you want to pause and write it down yourself. But we get kind of the familiar sine and cosine. It's normalized so that the speed is 1, right? So once I got my x value, then I can get the y value. So that was, I didn't really slow down for the work there, but you can do it. But again, for the same curve, there's a unique arc length parameterization up to where you start and what direction you go. So for the one I did with the square root of 1 minus x squared, or r squared minus x squared, then when x is 0, I'm up here. And so that was my starting point, and I'm moving counterclockwise. So if I start that way, this is the way to parameterize that with respect to arc length. You can check the dx ds and dy ds is 1. But, I mean, if I want to start here, then I could use this parameterization. Or if I want, generally we start here. So x is cosine, y is sine. And you usually don't worry about an arc length parameterization, so it's usually just x is r cosine t, y is r sine t. But then your speed won't be 1. But if you want your speed to be 1, you have to divide this by the radius. And then how far you've gone is where you are on the curve, or will get you where you are on the curve. So again, so those were 2 arc length parameterizations that we saw. I didn't really go slowly on the maple, but the video is already long enough. I'll just lastly again mention, in theory, every curve has an arc length parameterization, but in practice, you're not going to find it analytically. But if you think about any curve, if you could just have something travel along that curve at speed 1, then wherever you are at any time, or any s, I mean, that would be the arc length parameterization. So 1 exists, you generally just can't find it in terms of elementary functions and so forth, known functions. It just exists numerically. You could always solve if you wanted to do it. And I've had to do that for an animation before. All right, so hopefully that helps a little with thinking about line integrals and average values of a curve. So thank you, and have a good rest of your day.